Hi everyone, and welcome back to Module 5, where we're talking about the different types of data analytics. All right, so in Module 5-7, Learning Objective 7 within Module 5, I want to take a moment and review some basic statistical concepts because we'll need them as we perform different analyses in subsequent modules. So let's start by talking about the differences between a population and a sample. So a population is a group of phenomena that have something in common and includes all relevant parts. A sample, on the other hand, is a subset of members of a population selected to represent that population. So historically, accountants have had to work with subsets of data, samples. But as data availability is increasing, as well as computing power, accountants are increasingly working with populations, entire populations of data, rather than samples of data. And so let me give you an example of this idea of population versus a sample, okay? So we might have a question like, what percentage of restaurants are closed on Sundays? So the population there would be the listing of every restaurant maybe in the United States. That would be the population of restaurants. But it's unlikely that we'll be able to gather data on every single restaurant in the United States. So what we can do instead to assess our question, to figure out an answer to our question, is we could take a sample, right? So we could take a statistical sample of restaurants that hopefully represent the broader population. So we're trying to figure out what percentage of restaurants are closed on Sundays. We can't possibly look at every single restaurant in the entire United States, but we want an answer to this question. So what we could do is we could try to predict or select a representative sample where the sample represents the population. We have a random sample and it represents the population as a whole. And we could assess our question using that random sample, all right? So that's the difference there between a population and a sample. We should also discuss the difference between parameters and statistics. So a parameter is a characteristic of a population, while a statistic is a characteristic of a sample. So for example, the average number of all restaurants closed on Sundays would be a parameter. And typically we represent parameters using Greek letters, like the Greek letter mu, right? So the average number of sampled restaurants closed on Sundays would be a statistic. So that would be a number calculated from our sample, which we call a statistic. And we typically represent averages from a sample with the notation X bar, right? We draw the letter X for a random variable and we put a bar over top and it represents the average of our sample, okay? So if we can't obtain data for the population, the goal is to select a sample in a way that X bar, our average from the sample, closely approximates mu, which is the average for the population. So if we select a good sample, we can get a pretty good estimate of what the population average is. And this is how polling of voters happens every year, not every year, but maybe every 4 years for a presidential election. They take a statistical sample, a representative sample of voters across the country to assess how the entire country might vote. All right. Also, I wanted to talk to you about different ways of trying to understand central tendency, which we will look at things like mean, which is average. We'll look at median. So if you have a sequence of numbers of say 1, 2, 3, 4, 5, the number 3 would be the median in that range. And then we would look at mode. So mode is the most repeated number in a sample. So all statistical concepts that we'll need in subsequent analysis that we'll be doing. We also want to understand the spread or variability of the data. So, how much does one observation vary from the next? You know, do we have data where one observation has a value of -5 and another observation has a value of positive 10 million, right? So what's the range of values in the data? And so we'll be using measures such as variance and standard deviation. All right, and now I think it's just to make sure we're all on the same page. What I want to do now is walk you through a measure of variance. All right, so let's calculate variance and standard deviation, and I'll see you in just a moment.
Hey everyone, in this video I just want to talk to you for a minute about measures of variance. So sometimes, or whenever we're working with data, right, we're going to have a set of observations, we're going to have a data set, and for certain variables in the data set, we're going to want to know how much diversity do we have in the sample. If we're looking at a company's assets, or multiple companies' assets, who's the biggest company in the sample and who's the smallest company, and how much variety in between the min and the max there do we have within the sample. And there's lots of different ways to measure that variability within the sample. We could look at what's the difference between the max and the minimum, and we can subtract the minimum from the max, and we could look at variation that way. Two statistics that are used to measure variability are variance and standard deviation. So in this video, what I want to show you is the concept behind these two measures. So on your screen here, I have just an Excel sheet, and I'm going to say maybe we have a data set that has 20 observations, right? So let's say, and we're measuring, let's say we have a variable, let's just say it's assets, right? And we have assets that go from 1 to 20, just to keep it simple. We're going to have the first observation has a value of 1, second 2, the third 3, and all the way up to the value of 20, right? So we have these 20 values in our data set. And let's calculate the average. So we're going to say average of these values is 10.5. And we also want to know how many observations that we have. So let's count these. We're going to use the count function in Excel. We have 20 observations, so nothing surprising there, okay? So we want to come up with a measure of how much this sample varies. And one way to do it would be simply to say, well, our maximum value is 20 and our minimum value is 1, and so one measure of variation is the range of 19, right? Our data has a range of 19 between the high and the low. Another way to do this is to say how much does each observation in the data set, how much different is each observation from the average of the entire data set? So this value 1 would be x, right? The x is representing an observation, a value of an observation. And x bar is what we call our sample mean, right? So we're going to say how different is 1 from the sample mean. So we're going to say take 1, right, and compare that to the sample mean down here. And we're going to want to copy this formula, so I'm going to make this, I'm going to add absolute references. So I'm going to put a $ in front of the B here, and then I'm okay with leaving 2 without a $ because I want that to move. And I'm going to add a $ between the B and the 23 here, because I always want to pull from the mean of 10.5. Okay? So this observation is 9.5 units smaller than the sample average. Okay, so there is a measure of variance for each observation in the sample. And as you go up to the top observation here, this observation is 9.5 units bigger than the sample average. Right? So this gives us some measure of how much each observation varies from the sample mean. And this is a measure of variance. Now the problem with this is we, if you were to add all this up, right, you get a value of 0, right? So if we sum this up, right, it adds up to 0. And that makes sense because, you know, we're comparing, we have some values that are negative, some that are smaller than the average, some values that are larger than the average. So we can't really get like a summary measure of total variance. So the solution to that is simply to square each of these values, to get rid of the negative sign on the negatives. So we're going to say, take this and square it. Okay. And we're going to carry this down. And now we have, this is a unit that we could add up, right? But the problem is sometimes, you know, we have big samples, sometimes we have small samples, so let's kind of scale this by how many units or how many observations we have in this data set. So instead of saying 90.25, that doesn't really have any context, it could vary based on, you know, lots of different factors. So let's kind of standardize this. Let's scale it so that we can compare it to different variances in different data sets. So we're going to take this value here and we're going to divide it by the number of observations minus 1. Now the reason why we subtract 1 is because of a concept called the degrees of freedom. It's not really important, but conceptually what we're doing here is we're scaling the variance to kind of standardize it. So we're going to take this value, right, and we're going to divide it by 20. That's the number of observations we have. We're going to put an absolute reference in here, minus 1. Right? And so our measure of variance for this first observation is 4.75. We'll carry this down. And let's format this so it looks nice. And the statistic that we're calling variance is simply the total, the sum of all these individual variances that we just calculated. So our variance is 35. And standard deviation basically says, well, you squared, right here, you squared these values, right? So you overinflated this. So if you want a deflated value of the variance, all you got to do is take the square root, SQRT, right? That's the function in Excel. Take the square root of the 35. And that will give you the deflated standard deviation, or I'm sorry, variance. Right, so our standard deviation is 5.92. All right, and if we wanted to check this, we wanted to make sure we had we calculated this correctly. We can use Excel's variance formula. So we can say it's called variance or var.s, which stands for the variance of the sample. We'll just highlight the original values, and if we did this correctly, we should get 35. Right? See, that's exactly what we get. So there's our variance of 35, and our standard deviation, we could use the stdev.s function in Excel, highlight the original observations again. We get a standard deviation of 5.92, just like we calculated here. But that's the idea. Because variance and standard deviation they're not very intuitive. But if you can try to think about variance and standard deviation as being this concept here, we're just trying to compare each observation in the data set to what the data set's average is. So how far from the average is each observation in the data set? And that's measuring how much variance we have on an observation by observation basis. And then the stuff we do here in columns E and F are really just scaling and things to deal with negative values. This is the heart of it. We're trying to understand how far from the mean or the average is each observation in the data set. That's what we're capturing there. Okay, and so this gives us an idea of how spread out the data is, and it's very useful in evaluating samples. All right, so I hope you found this video helpful, and I'll talk to you all soon.
All right, welcome back. We just went through our video of variance explained, and let's move next into something called probability distributions. What are probability distributions? So a probability distribution is a statistical property that describes the possible values and likelihood that a random value will be in a given range. So a really useful distribution is called the normal distribution. And so if you've ever seen a bell-shaped curve, The bell-shaped curve in a graph, it represents a normal distribution. It's a probability distribution where where the distribution of values is symmetric around the mean, with data points closer to the mean more frequent than those further from the mean. We use the normal distribution to do a lot of statistical tests, right? So we're going to make assumptions in our statistical tests that are based on the normal distribution. Let me give you an example. So mean IQ score is 100, right? So the average person has an IQ score of 100, and the standard deviation is 15. So Albert Einstein had an IQ of 160, right? So that's genius level, okay? So using the normal distribution, we could calculate something called the Z statistic. And the Z statistic takes the value of Albert Einstein's IQ, which is 160, and subtracts from it the average IQ, which is 100. Right? So Albert Einstein's IQ was 60 points higher than the average person's IQ. Okay? So now we have like a measure of how far or how much above the average Einstein was. And then we're going to scale it, right? Because not all values are going to be on the same scale, and so we're going to scale it by the standard deviation of our sample. Right? So the standard deviation is 15. So on average, it could be plus or minus 15, 100. Right? So the average IQ is 100 plus or minus 15. So the range of 85 to 115 is where most people fall in terms of IQ. So we can translate that for Einstein into a statistic called the Z statistic. And so if we take his 60-point variance divided by the deviation of 15, that is telling us Einstein was 4 standard deviations higher than the average person. 4 standard deviations, all right? And so we'll be using Z statistics in some of our tests here in the data analytics course, and so I just wanted to introduce that a little bit to you. There are other types of distributions. For example, we'll primarily be working with the normal distribution, but there's also something called a uniform distribution where every observation in the data has the same exact value. There's also something called the Poisson distribution, and Poisson measures like the average number of events that occur over a period of time. And we'll be using all of these, we'll be using primarily the normal distribution to look at something called hypothesis testing. So in hypothesis testing, data is used to answer questions and test hypotheses. For example, sales at our stores are higher on Saturdays than on Sundays. So the way to think about this is, in science and in statistics, we always present hypotheses in pairs, right? So we have something called the null hypothesis. The null hypothesis is the assumption that the hypothesized relationship, and so remember our hypothesis was that sales were higher on Saturdays than they were on Sunday. So it's an assumption that that hypothesis or that relationship does not exist, right? So it's like the burden of proof, right? So if you ever watched a movie that involved courtroom or law type of concept in the show or in the movie, you've probably come across this idea that if somebody is being tried for a crime, the burden of proof is on the plaintiff or on the prosecutor. We have to prove. So the assumption is that the defendant is innocent, right? Innocent until proven guilty, right? We have to prove that the suspect committed the crime, and if we can't prove that, then the defendant is free to go, okay? Well, think about hypothesis testing in the same way. So we're gonna have innocent until proven guilty. That's the null hypothesis. We're assuming that our hypothesized relationship is false, right? There is no relationship between the day of the week and the level of sales. Now, the alternative hypothesis is the opposite. So we do believe, we're trying to prove that sales are higher on Saturdays than they are on Sundays. So our job is to disprove the null hypothesis. We're trying to gather evidence that is inconsistent with the idea that there is no relationship between the day of the week and sales. All right, and we'll do this through hypothesis testing. There are some statistical tests that we'll be using. We'll be using p-values. And so a p-value is the probability that we could obtain our test results if the null hypothesis that we just talked about were true. So let me give you another example. So suppose we're flipping a coin. What's the probability that we would get 90 heads in 100 coin flips? That seems pretty improbable, right? We have a quarter, we're flipping it 100 times. What are the odds that we're going to get 90 heads in 100 flips? So if the coin is fair, right, it's not like somebody didn't rig it and weight it in some way so that the heads come up more frequently. We have a fair coin. A fair coin should result in about 50 heads. The alternative hypothesis that we're trying to test is that we don't have a fair coin. Okay, we flipped the coin, we got 90 heads. Our hypothesis is that coin has been messed with. Somebody messed with that coin, right? The null hypothesis, the hypothesis we have to disprove, is that that coin is fair, okay? So let's think about this in statistical terms. If a fair coin was used, right, we had a fair coin, the probability of that coin generating 90 heads is 0.00000014%. 0.0, it's so, the probability of that happening is so small, right? It's possible. You could have a fair coin, you could flip it 100 times, and you could get 90 heads. That will happen, right, from time to time. But the likelihood or the probability of that happening is 0.000014%. It's minuscule, it's tiny, right? And so in our hypothesis test, we would say, well, it's possible, right? You could have a fair coin, but the weight of the evidence suggests we don't have a fair coin, right? The probability of that happening is so small that it's unlikely that we're using a fair coin. We would reject the null hypothesis. We would say, that hypothesis that you have a fair coin, that hypothesis is false. We're going to accept the alternative that this coin has been messed with. It's been rigged, all right? So it's a way of testing whether or not something is true without absolute evidence, right? So it's possible that we have a fair coin, but it's highly, highly unlikely. And usually we can accept that we don't have a fair coin in this case. But at what level can you accept that, right? So what do people typically do? Let's say the probability that we had a fair coin came out to be 15%. Right? Would we still reject the hypothesis that we have a fair coin? Would we still conclude that the coin has been messed with? Well, probably not. The 15% probability that the coin is fair that's a pretty decent range. So what we do when we do hypothesis testing is we set an alpha threshold. What is the level of probability that we would be most comfortable with? And so usually the alpha threshold is set at 5%. Right? If the probability of something happening is 5% or less, we're going to reject the null hypothesis. All right? And we can use this alpha threshold to generate something called confidence intervals that you can read more about on our lecture notes website. We'll also be interpreting statistical output from t-tests of different means. And so a sample t-test is a statistical test used to compare means of two data sets or data observations. All right? We could have a paired t-test. So basically we have two samples and we want to know if the means are the same. Give me an example, okay? So say a company wants to know if its sales returns are higher around the holidays than at different times of the year. The company collects sales data on returns and then breaks it up into holiday and non-holiday times, and they calculate the averages. Right? So you have average returns during the holidays, average returns on non-holidays. and there's a difference, but can we conclude that the difference is large enough that there actually is some type of relationship there? And so to evaluate that, we can use a t-test. And the t-test uses the normal distribution to evaluate whether or not two averages are the same. We could also use regression. And so regressions are used to help measure the relationship between one output variable and one or more input variables. And regression is actually, it's pretty simple. It's all based on this idea from your Algebra 1 classes that you probably took in high school. So Algebra 1 gave you that formula for a line, right? So if you wanted to draw a line between two data points, you would use the formula y equals mx plus b, right? So we're going to take that idea, and if we have a set of data, we have an input variable, right? So maybe SAT score is our input variable, and college graduation rate is our output variable or our outcome variable. So we're trying to predict whether or not a student will complete college based on their SAT score, right? So our x-axis is SAT score, our y-axis is college completion rate. We collect data on a whole bunch of different students. We plot the different data points, SAT score 1200 versus completion rate, yes, right? So, and then we have all these data points in a graph, and we can draw a line through it using this idea from Algebra 1. And so what the line does is it tells us, is that line, does it have a positive slope, right? That m in the y equals mx plus b, is there a positive slope? Or is there a negative slope, right? As SAT score goes up, is there a lower completion rate? And what we're trying to do is determine if there's a directional relationship between SAT score and college completion rate, right? So we're not necessarily trying to understand like the size of what happened, but maybe if there is a relationship, is there a directional relationship between our two variables, all right? And there are a bunch of statistics in this output, a regression output, that we need to interpret. And in one of the labs, I walk you through how to run a regression in Microsoft Excel and how to interpret the output, all right? So we've reached the end of learning objective 7 in module 5. And so the idea here was to just give you a refresher on some statistical concepts, because we'll be using these concepts in later modules. So hopefully this video was helpful for you in catching up on your stats, and take care. I will see you soon.